So when we talk about conductors versus insulators, this is an important consideration too with this unit. If you look at this picture, we have some good examples of conductors and insulators. And the skillet is an excellent conductor. It's conducting, energy from the plate to the food there. But then, he's protecting his hand with this insulator that, you have this glove here. And what's a glove, filled with? Sure, there's insulation in there, but it's filled with a lot of air. Air is actually a great insulator. It doesn't transfer energy very easily. So if you have a thermos, a lot of times what they'll do is they'll just have inside a bunch of air. You got your liquid in the middle, you got your cap on top, but all around this is just air, and it's a good insulator. So transfer of heat by touch we consider as conduction. So that's one way that we transfer energy. And this is a picture of a burner that is heating up a metal bar. And what's happening is these molecules in here are hitting the other ones, and then they're hitting these, and then they're hitting these, and then they're hitting these, and then they're hitting these. And it transfers this energy all the way through. And that's by touch, by conduction. So with this house here, you can see that there are different areas where thermal energy is being transferred out of. You got your windows, and then the side of the wall, and then the top of the house. And so, as construction or designers and, folks making the homes, they have to pay close attention to that, and to minimize the transfer of energy in or out depending on the needs. So thermal insulation is rated for a certain R value, and the length per thermal conductivity we deal with there. So we have the different substances here. R value of glass here is 1, whereas you have fiberglass, which is higher, and then other substances. If you notice here, like with this insulation R of 30, that's much higher. And so so the different thermal insulation is used for different situations. And so as you consider the thermal conductivity of these different substances, some transfer energy more effectively than others. And so in this case here, there's just different uses or costs, right? You have bigger windows, you can have more energy lost. So transfer by convection is where heat flows from one place to the other by the mass movement of molecules from one place to another. And so convection is you can see that in this pot here, right? So the warmer water rises, the cooler water descends, and we have that that flow around. And then heating by convection, we have the molecules coming up, going down, coming up, coming down, and here, but also in homes, right? So you have the hotter air rising, the cooler air descending, and you have that transfer around. In fact, in your house, you have fans, right? And so these fans, we're used to using them in the summertime, where we can cool off, but you can actually use them in the wintertime. We know that that hot air rises, and so there's a little switch on your fan that if you click it, you can reverse the direction of your fan, and it can actually blow the air back down from the top and cool down the room, or heat up the room rather, in the wintertime. The last of the 3 ways of energy transfer is radiation. And so electromagnetic radiation we're going to spend a lot of time on in a later unit, but the one we're most familiar with and the one that we're most reliant upon is the radiation from the sun. The sun is burning at average 6,000 Kelvin, which seems very high to us, which it is, and we're receiving those electromagnetic rays from the sun. And it turns out with electromagnetic radiation, if you heat up this horseshoe, for instance, it's glowing, right? And so it's at a certain temperature, it's glowing. And so we have that. We actually have that with different objects, you know, with at certain temperatures, you know, they're sending out certain electromagnetic waves. And so, you know, infrared, we're actually all shooting out infrared from our bodies right now. We all have a certain temperature. And if you had an infrared camera, you've probably seen those. If you want to do a quick Google or YouTube search, look up infrared camera, you'll see lots of examples where you can actually see what can't be seen. We know that the infrared electromagnetic rays are just before red. We can't see them with our visible eyes, or they're not visible light. We can't see them with our eyes. But you know, if we have a special camera that can detect them, that will you know, show us the different electromagnetic rays from that spectrum. So here's an example of you know, taking a picture of a person based on the infrared coming from them. They have a certain temperature. When we also talk about light in terms of what's happening in this section, the absorption of light is very much dependent upon, you know, the substances here, right? So if you have light hitting this white surface, the snow, it's just going to reflect right back off, most of it. But when light hits this, when it hits the, you know, the pavement or concrete, a lot of times it's absorbed, especially if you have asphalt. And so it's absorbed, that light's absorbed, and then it's also radiated out as well. And so a good absorber is also a good emitter. And when we talk about this, we talk about emissivity, and that's the number between 0 and 1 that gives a proportion of how effective it absorbs or radiates heat. And so coal is very close to 0. It absorbs, you know, absorbs light really well. It also sends out thermal energy really well. Metallic surfaces like this here are just going to reflect it. It's not going to absorb, or, you know, if you turn off all the lights, emit energy from it. So when we calculate black body radiation, we can do that by multiplying the emissivity. And again, you know, certain substances have much higher emissivity than others. We have the Stefan Boltzmann's constant here. And then we have the area that's exposed. And then we have the difference in temperature. The greater the difference in temperature between the substance and the outside, the greater the power, the greater how much energy or heat in a period of time that we're going to have coming out of it. And so in this first example that we're going to look at with the dog walking at night, their emissivity is 0.7, and the dog's temperature is 39 degrees Celsius. And in this case, we're going to figure out first what's the power output of this dog. And then, yeah, we can figure out the total amount of energy lost in 20 minutes. Now, as you set this up, and here's the dog, right? And we've got, we have to have our temperature in Kelvin, so you have to be careful with that. And then you're going to do the temperature calculation first. You're going to take the temperature in Kelvin of the dog, 39 plus the 273, and then take that to the fourth power. Then subtract, you know, the outside temperature, 2 degrees plus 273, take that to the fourth power before you do anything else. So why don't you go ahead and calculate the power output first, and then once you do that, we'll check that, and then we can do the second part. So go ahead and pause the clip and try that, and then when you're ready to check, you can hit play to continue. Okay, so we've got that. Our values, we should get, multiply those, we should get 96.92. Now what I want you to do is go ahead and try, you know, in 20 minutes, how much energy does this dog lose? If this is the power output by the dog, thermal energy, you know, how much energy is lost in 20 minutes? So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right, so power is energy and time. 20 minutes would be 1,200 seconds. 96.92 watts is the power, and so the total amount of energy, 116,304 joules, would be how much energy this dog would lose in a 20-minute walk if that was the two temperatures.